Hi, everybody. We're going to talk about absorption and transmission loss, and I'm hoping to do a live demo for you here. Hopefully you can see the impedance tube set up in the room here, and we'll take you through quickly a live measurement and show you how it works in test lab. In terms of an agenda, we're talking about absorption and transmission loss, and from a big picture, you talk about those and you think about those two things in an effort to control sound. So the overarching topic here today is sound control or sound noise control, if you want to think of it that way. And two of the tools we have at our disposal is absorption and transmission loss. So these could be for materials development, so foam or carpet, materials you have to absorb sound. And it can also be transmission loss, which could be a barrier, like a wall in your apartment building or an office building, or it could even be like a muffler or an acoustic duct that you have between your source and your receiver. Transmission loss is one of the tools we use to quantify how well that muffler or that duct system is working. So we'll talk about some basic principles of these two quantities, and then we'll take a brief overview of some of the techniques we use to quantify absorption and transmission loss. So the basic principles, some vocabulary we'll need throughout our day today is some different acoustic fields. You have free field, which is sort of exactly what it sounds like if you picture yourself standing out in the middle of an open field and there are no buildings or trees or anything for the sound to bounce off of, and you shouted or you clapped your hands, that sound, these sound waves would leave you and propagate out in a spherical wave front, and it would just kind of go on forever. It would never hit anything, so there would be nothing to create a reflection and bounce back. In acoustics, we call this the free field. It is free of reflection. All of the sound we're measuring is directly from our source. Now, we don't obviously have the ability in a laboratory setting to ensure that we're not going to have any reflections by having a huge empty environment. And so what we do is we approximate the free field by trying to absorb these sound waves before they have a chance to reflect. And so you get something like these walls and the floor and even the ceiling are covered in these acoustic absorbing wedges. This is what we would call an anechoic chamber. No echo chamber, if you want to think of it that way, where we're absorbing those sound waves before they have a chance to bounce back. If we're working on something like an automobile that's always driving on a hard reflective surface like the street, it's more appropriate for us to test in a what we call a hemianechoic or half anechoic chamber like you see on the bottom right there. So that's no reflections, and the opposite is what we call a diffuse field, where on purpose we're creating a chamber that has as much reflection and creates as many reflections for our sound waves as possible. And so we often have sort of thick, robust walls that are very stiff and massive, and the finish on these walls is typically something very smooth to encourage the sound waves to bounce around as much as possible. And you can see in the illustration, even the walls of the chamber aren't at right angles, so there's no parallel walls where the sound can be just sort of bounce back and forth and cancel itself out over time. You have all these sort of odd angles so that the sound bounces around as many times as possible. And if we were to measure in this diffuse field with a microphone, we'd get the exact same sound pressure level reading or even an intensity reading with an intensity probe anywhere we went in this room. We want the sound to be perfectly homogeneous in every direction and every location. And we use this diffuse field to approximate situations where the sound is coming from all around you. So if you drove in a car today or you're going to ride in an airplane, your seating position in those vehicles, you have sound reaching you from all different directions, in front, behind, above, below. The sound's just sort of coming from everywhere. And so we think of those environments as being diffuse fields. And they may not be perfectly diffuse, but close enough as a description for us to get a working knowledge of that environment and make some good decisions. Free field, no reflections. Diffuse field, all reflections. Essentially can't tell where the source is coming from because the sound is coming from everywhere. Also important for us during our discussion today is the angle of incidence. So there's direct incidence where the sound waves are all coming perfectly normal to the surface of our material that we're testing. This could be a barrier, this could be a coupon that we're sampling, like we'll look at in a little bit here. But the sound waves are coming 90 degrees from the surface that we're testing. That's direct incidence. Random incidence is we want the sound to be coming and approaching and hitting that material from all different directions and angles. So it's not just directly in front of, but off to all these sides. And so we want to test how the sound is going to be affected by the material as it's coming in steep angles as well as normal incidence. Okay, so that's random incidence. So sound absorption. So here's our sound sample, or our sound absorbing or barrier material that we want to test. And let's say we hit it with some sound. Now, one of three things is going to happen in different portions depending on the material properties of our sample. Some of that incident sound wave might bounce off and be reflected back. Some of it may be absorbed by the material inside and translated into heat. And some of it might make it through the barrier and be transmitted right on through. Okay, so essentially the green, the yellow, and the blue are all going to sum up to the incident power that we had in the initial red arrow there. Okay, so it's either going to be reflected, absorbed, or transmitted. Now, when we're talking about working on a material to increase the sound absorption, we want to focus on that yellow part where we're taking that sound pressure wave and we're breaking it up and we're turning it into heat through friction. Okay, and that's absorbing it so that it gets trapped inside the material and turned into heat. We're talking about sound transmission loss. We're worried about minimizing or controlling the sound that gets through and quantified by that blue arrow. Okay, so some sound's going to get through, something like a muffler or exhaust system, or even like a door or a window or some other sort of barrier. But we want to control maybe the frequency content and maybe the amplitude of the sound that gets through. Okay, so absorption, we're talking about quantifying the yellow. Sound transmission loss, we're talking about quantifying the blue. So with absorption, what is it? We give it this coefficient of alpha typically, and it is just the ratio of the incident power and the power that is reflected. So the amount that's reflected divided by how much was originally coming in, and then we subtract that ratio from 1. And so alpha is always 0 to 1. It's never greater than 1. And closer it is to 1, the more a perfect absorber it is for that frequency range. So typically something like an open cell foam or a carpet or something will have a high alpha where this is saying approximately 90% of the incident sound power that was hitting the foam gets absorbed and only 10% of it bounces back. Whereas something like a brick wall, you have less than 10% maybe that's getting absorbed and almost all of it's being reflected back. Okay, so different materials have different alpha values, and these are some very generic values you're seeing. Obviously 6mm porous rubber sheet, that could be a number of different varieties. We're saying on general it's not a very good absorber, and we're also sort of giving you an averaged value over the frequency range. As we'll see, alpha and sound transmission loss are quantities we do versus frequency. It's not the same per frequency band. So giving it one number is really kind of averaging upon an average, and it's really just a generic number that isn't incredibly useful for an engineering purpose. So with sound absorption, the effect of material thickness, so if you look at absorption coefficient, again, higher is better on all of these plots. You'll see this blue arrow. The higher you are on this chart, the more sound you're absorbing with your material. And then you see versus frequency here. And we have a 30mm sample of foam, let's say in this case, and we get this purple line, and that shows us versus frequency how well we absorb the different frequency noises. As we make that material thicker from 30mm up to 50, you see a tiny bit of improvement in the high frequency, but really pretty dramatic improvement in the low frequency range just by increasing the thickness. And that sort of makes sense, right? As we go lower in frequency, the wavelength or the space physically or in distance wise between the peaks of our pressure wave gets further and further apart. And so the more material we have to absorb that sound, the better it's going to work at those longer wavelengths. And then you see we more than triple the original value all the way to 100 millimeters, and we get very drastic improvement at the low frequency. Helps everywhere a little bit, but really important to help our low frequency concern. The higher frequencies are always the easiest to absorb just because of those short wavelengths. And open cell foam, you know, the cells of that styrofoam or that carpet are pretty big compared to the wavelength of the sound at 8,000 hertz, at 10,000 hertz, right? So those are very short wavelengths. But as we get lower and lower, those features of the material get smaller and smaller comparatively. So that's why you have to increase the thickness. One of the tricks you can pull with absorption for a given thickness is you can mount it with an air gap behind it. So if you see in our example here, you have a hard reflective surface like a wall, a brick wall, but we're mounting our foam or our acoustic panels if you're in a recording studio or something. If you put that, let's say this is 1 inch of foam, just for example's sake, and we look at how well this 1 inch of this foam absorbs, we get this yellow. And it's not bad, but again, it's not doing very well at low frequency, below 1,000 hertz. If we take that same sample and we move it off the wall, in this case by 1/2 inch or so, 3/4 of an inch maybe, just by increasing that air gap, we'll see a low frequency improvement with the same exact piece of foam or wood paneling or whatever it is, just by creating that air gap in the back. Now, why would that be? Well, if you think about the mechanism that we're talking about that absorption works by, we said we're taking that pressure wave and we're actually deconstructing it and breaking it apart and turning it into friction, right? And so if you rub your hands together, you know the faster and the harder you push, but the faster you rub them together, the more heat will get generated, right? It's a velocity-based thing to generate heat through friction. And so if we think about how the air molecules are working in our example here, where we have our wall on the far left, and that's rigid, right? So the air molecules shown here by these little gray dots don't move a whole lot, right? The velocity at the surface is 0. But if we were to play a single frequency, in this case, I'm just showing a single frequency, but we play a sine wave in that recording studio and it hits our wall, and that sine wave is going to mean that our pressure is going to go up and down, and it's going to go between a maximum and a minimum, right? And where we see those maximums and minimums, the maximum pressure is when those air molecules are being squeezed together, and then the minimum pressure is when they're being stretched apart the maximum amount, right? Well, there's some portion in the middle between those two where the pressure is essentially always 0 because those molecules are just moving back and forth. They never really get squeezed and they never really get stretched. They're really just moving back and forth and doing the squeezing and stretching. Okay, so you see these blue molecules we're saying are nodal molecules. Those don't move at all because they're at an area of maximum and minimum pressure, just like at the wall and right here in between. And then you see these red molecules are highest velocity, if you want to think of it that way. The lowest pressure oscillation, but the highest velocity. And so by moving that sample off the wall, we are putting it where the air molecules are moving the fastest and the most for that frequency, okay? So if I butted this same piece of pink foam up against the wall, it's still going to absorb, but it's not going to do nearly as well a good of a job because the air molecules against the wall just aren't moving as much as they are out here, okay? And so we're going to maximize the velocity of the air particles, which is going to increase the friction, which is going to change more of those pressure waves into heat, and as a result, in more absorbed sound. Okay, so that's why the air gap thing works. Now, as far as sound transmission loss, this is another ratio, and it's really just the incident power, so our W sub I, our red power on the first half of our barrier, and then reference that or ratioed to the transmitted power, W sub T. It's a logarithmic ratio of those two sound powers. And so the drop in that ratio, the lower the transmitted power is, the higher our transmission loss will be. So some examples and applications, talked about mufflers. We want to make our engine noise in the combustion events the explosions going on inside the combustion engine. We want that to be as quiet as possible, so as much of the sound to be reflected back or absorbed, we don't care, as long as it's not coming out the tailpipe, right? And then something like a door or like your apartment wall, you would like to not hear the neighbors above or below or off to the side, and so we work on those barriers in terms of transmission loss as well. And so something like a sound barrier. Now, when we look at sound transmission loss, for example, this simple expansion can here, so it's really nothing but a radius change. You have an inlet pipe, and then it gets bigger, and then it goes back to the outlet diameter. And you look at the sound transmission loss, and again, higher is better on this chart. And versus frequency, you see there are some places where it does really well, 20 dB of sound transmission loss. You see that sort of repeat. But you see these drops in the sound transmission loss, right? So if I look at this and it's about 750 hertz, double that is 15, triple that is 2250, right? So there's some harmonic thing going on here, and that has to do with the geometry of this particular expansion can. So that 750 hertz drop in transmission loss is because the sound that's the natural frequency of the air cavity in that expansion can based on the dimensions, okay? So the air is really good at moving back and forth at those three frequencies, and as a result, the sound goes right through, or even is helped and gets magnified by the expansion can. So you'll always see sort of these areas where it's really good, and then places where it's not quite as good, and that's based on the geometry. And that's why your muffler or your exhaust system isn't just a simple expansion can. There'll be a series of expansion cans and perforated tubes and different chambers, and it's a much more complicated device than just a simple single expansion to cover more of these frequencies more equally. So that's transmission loss, and we see some of the same trends where if we have a barrier, you make your walls twice as thick, the sound transmission loss is going to improve, right? More of the sound is not going to make it through. And so the thicker you can make it, the better. The more massive you can make it, the better. That's going to help block and or absorb the sound and keep it from getting through. If you have a very large wall, you need to consider that that is basically a big plate, right? And it's going to have its own natural frequencies where it wants to bend back and forth. And just like our expansion can had a natural frequency where it liked to oscillate in between, that wall, if it gets big enough, or any wall will have a natural frequency, but if the wall gets big enough, that might drop into a frequency we care about, where all of a sudden, in this orange line, there's a drop in the transmission loss because right here at 800 hertz, that's where the barrier wants to oscillate in a bending mode, and it actually helps the sound get through. So you'll sometimes see these dips in transmission loss, and they almost always have to do with some sort of resonance of the structure or the acoustic volume for something like a duct. If you're applying treatment to, say, an automotive front of dash or a floor pan in a vehicle, and you're using some spray-on damping or some other material, you have to be very careful and manage your pass-throughs or any holes you have in that barrier for steering column. Steering shaft goes right through the front of dash, air conditioning lines, things like that. These all have to go through that barrier, and there are opportunities to develop leaks. And so if you had full coverage with this acoustic treatment on a solid metal panel of this given thickness, you'd have this nice transmission loss that would go up versus frequency. However, if we introduce a very, very small leak, so 1% of the total surface area, tiny little leak, you see how dramatically compromised the sound transmission loss is. And so as that leak gets bigger, it's just going to get worse and worse. So a lot of attention is paid to sealing those leaks and making sure that you're keeping the sound and keeping your barrier continuous. If you have gaps underneath your doors in your house, you might have noticed that if you have almost any gap, it's like that door is not even really there, compared to if you have carpet or something, that door makes a better seal to the carpet. The door actually works as a pretty good sound barrier, again, depending on its design and things. But if you introduce a gap at the bottom of that door, the sound just finds that weakness in the barrier and goes right around the door. So something to keep in mind. And similarly, if you have damping material like we were talking about, if you have to leave a part of that panel exposed, you're just compromising the effectiveness of that damping material in terms of helping your barrier be more efficient. So again, you do your best to optimize the placement, coverage, and minimize leaks. That's some of the fundamentals or basic principles of absorption transmission loss. Let's talk about the techniques we use to quantify these. And I'm going to talk about two different areas. We have small samples, for which we're going to use this thing called an impedance tube for both absorption and transmission loss. And then for large samples, so maybe it's a bigger piece of carpet, maybe it's even something, a full assembly like a couch. We want to know how much our couch is going to add to the absorption in a given room. We might have larger samples where we'll use some different approaches, either a one room or even this thing called an alpha cabin. And then for transmission loss, we need two rooms and they need to be connected to each other so that we can put our sample right in between the two. And I'll talk about the different ways we do that. Up first, let's talk about absorption in an impedance tube. So an impedance tube is a piece of engineering equipment. It's made with thick walls, typically brass or something that's very thick and massive. And at one end, we have a speaker that generates broadband noise at all frequencies and then sends that sound energy into the tube. And the reason the walls are massive and thick is because we want to trap all of that sound inside. We don't want it vibrating the walls of the tube and some of that sound energy getting out. Because what we're going to do is we're going to send that sound down the tube right toward this end where we have this rigid termination or very stiff wall at the back. And then we also have our material sample down here. So we're sending a bunch of broadband noise down this way. It's going to hit our sample, hit that rigid termination, and some portion of that incident sound is going to bounce back. And these things here are microphones, and we're going to measure multiple microphones. So we have an idea of the sound intensity going this way and then the sound intensity of the reflected wave. And those two microphones will allow us to get the phase information and know which way that sound wave is traveling. And so we can compute the incident power and the reflected power and generate an alpha right from that. So that's an impedance tube. Some considerations we have when using an impedance tube for this type of measurement. First and foremost is providing a precision cut. And so if you purchase an impedance tube that Siemens sells, it will come with one of these sample cutters that you can use. You put it in a drill press or something like that, and it spins around, and this edge right here is really sharp, and it's engineered to be exactly the same diameter as the impedance tube that we sell. And so you can cut your own samples of foam or carpet or whatever it is that you have. Some places who do this for a living, like material manufacturers and that sort of thing, will actually have laser cut foam and material so that it's very, very precise and very, very repeatable. And then you have to take some care inserting this into the tube and making sure it's positioned correctly. And I'll show you some of that today during our demo. And there are some things we want to avoid. And part of that precision in our cut is that we can avoid these two semi-common mistakes, and that's having the material be too large, and so we're actually squeezing it sideways and compressing it a little bit to fit inside the tube, or the opposite problem where maybe it's a little undersized and you see we have this little air gap between the material and that rigid termination in the back. So as far as the sound wave is concerned, it's going to look at this and I could bounce off of that, but some of my energy will be absorbed, or I can bounce off this rigid wall in the back, and it's going to do both of those things, and you'll be fooling yourself thinking you're measuring just the effect of the material if you have that gap. So one of the things that we suggest as a best practice is to, even if you have a slightly undersized or even appropriately sized sample, is to coat the outer circumference with something like petroleum jelly or something that will provide a seal. So even in this example here, it would go all the way around in sort of an equal thickness, and then that sample would at least be held center, and that petroleum jelly would provide an air seal and prevent any of the sound waves from hitting that rigid termination in the back. This I'll show you in the software, but these are just the steps we're going to use in the software, and I'll take you through that in just a second. And then we're going to make our measurements and average those runs, and we'll get an absorption coefficient out. So absorption using an impedance tube, and I'll show you this in SimCenter Test Lab. And For sake of brevity, I've already started my project here, but I'll show you what I started. Let's see if I can end that. And so if I open my test lab, in this case 2306 folder, in this acoustics folder here, you'll see sound absorption using impedance tube. So it's a dedicated product. It's sort of purpose built for what we're going to do. And so if you start that up, it will start and be something, let me get some of these windows out of the way, something like we see here. So it'll automatically populate 2 channels in your channel setup, input 1 and 2. It sets input 1 as your reference. It calls them mic A and B. I had to set them to ICP based on the kind of microphones that I have in my setup, but it knows their pressure and it puts in an initial default sensitivity. Now I'm going to read TEDS, or the transducer electronic data sheet here, so that I can read the cal value for these specific microphones. So you see I select these 2 channels and I say insert, and it ports the real sensitivities of these microphones over. So if I go back to channel setup, you see the actual sensitivity has been updated, and this will give me a much more accurate measurement. I've got an 8-channel front end here. I can also just simplify my view by clicking this show on button, and it'll remove any channels that I don't have turned on. This is just a good sense check that, yep, I've got 2 channels turned on, mic A and mic B, and mic A is my reference. So that's all we have to do in channel setup. Next, I go all the way over to this absorption and tube. Now you could calibrate, certainly, if you've got a microphone calibrator and you want to improve even this sensitivity for the microphones from the factory, you could do that. I'm going to skip it today. We're going to go all the way to absorption and tube. And like I said, this is a purpose-built focused task module of Test Lab. And so all it does is absorption in tube testing. And so it helps you lead you through the steps you need to take and get a good answer. So in this case, our first step is this tube setup portion here, and I can click on this drop down and you see we have several tubes. In this case, for my test today, I'm going to be doing the high frequency test, and so it knows exactly the spacing between my microphones. And so if I show you over here on the actual tube, you see I have 3 microphone placements. If I was testing the low frequency range, I would use the wider spacing here to again capture lower frequencies. In this demo today, I'm going to use these 2 closer spaced microphone spacings, and that's going to make it more appropriate for measuring in the high frequency range. So I set that to Mechanism 34.9 high frequency, and it's got all the dimensions and everything right in here. If I've got my own custom made tube or something from another manufacturer that we don't have built in here, I can put all of those details in and it will work just as well. Now, the next step is to do what we call a phase calibration. And so because we're measuring the intensity between these 2 microphones, we want to do some measurements to understand exactly how our test system, the cables, the microphones themselves, the channels I've chosen to use on this particular SCADA's front end, how all of those things are going to affect what we call the phase relationship of our measurement. And so we're going to do some quick test measurements to sort of calibrate that and make sure we understand the effect of our system. And so in this case, I'm going to first measure this transfer function H21. Okay, so you see in this little diagram, my sound source is on the left, my sample would be on the right, and it's saying my microphone A, or my reference, should be closest to the sample or furthest from my speaker. So I'm going to go make that change in my real tube here. You see I've labeled my microphone A so that it's obvious which position I've got these in. Because we do a little bit of switching, it can be easy to make a mistake. So all I do is I loosen these collets and the microphones pull right out. And so I'm going to put microphone A in that position furthest from the speaker or closest to the sample. Tighten that down, and then I'm going to put my other microphone in this speaker close position. Okay, tighten that down. So now A is over here, and I'm going to plug in this attachment. So these 3 pieces of the tube would come with a purchase. This is the speaker, microphone holders. This is what we call an anechoic termination. So there's a bunch of foam in here and then a rigid termination. Essentially, the foam is engineered so that all the energy that enters here gets trapped or absorbed by the foam. And I'm gonna hook that up. So I just slide that in here and I just put these clips on and I'm ready to go. So now I'm gonna come over here. I'm gonna say measure H21 and it will automatically click me over to the measurement tab. It's gonna do 100 averages in this case. And it's going to take me through that. You see the instantaneous FRF over here, or the average FRF. It looks pretty flat, which is kind of what we would like to see. The more curves and activity you see in the trace here, the more difference there is between my microphones. And then this down here is my coherence. So you see it's basically perfect all the way through my measurement range. This big spike you see here is the upper frequency limit of the tube. So there's a natural frequency again of the cavity in there, and that's what we see here. And so the tube is only registered or valid up to a frequency up to about here. So you're always keeping the geometry of your tube in mind because every tube is going to have its own frequency that you want to measure below. Okay, so I've got that done. It'll now kick me back over here and I see my H21. Now my next setup is to go H12 and you see I'm just going to change the order of those microphones again and my mic A will be closest to my speaker. So I'll do that real quick. And these mics slide in and there's a nice positive stop that tells you you're in the correct position. Got that mounted in there, and now I'll measure H12. And so I've measured a transfer function with the microphone swapping positions, and that allows me to sort of quantify the phase difference that would be added to my measurements just because of the microphone, the cable, channel 1, microphone cable, and channel 2 on my SCADIS. And so by measuring it both ways, I can calculate what they call an HC or a correction FRF, and that will help remove that from my measurement and give me a more accurate absorption coefficient. So just a couple of averages left here. Okay, and now I can calculate HC, or the correction between those two. Okay, so this is my correction across the bottom. Okay, so now I've got my phase calibration done. Now I'm actually going to measure my samples. So you notice I did all of that with what we call the anechoic termination on there. I'll take this guy off. And now I'll use this other attachment. And you see it's got this plunger and this digital measurement device on here. And so you see I can pull this, and this is a plunger that moves back and forth. So this is the sample I'm gonna measure, and you see it says ref on here. So when we purchased the tube, they made a measurement with this sample itself and then provided us those results. And then we can test that sample with our tube and know that we're getting the right answer. And so I'm going to set this to 0. I know that this reference sample is 27 millimeters thick. And so I can 0 this out when the plunger's bottomed all the way up. And I'm going to move this past 27. I'm going to carefully put my sample in here so that it's past this lip here. You see it's in there more than, it's sort of recessed in there. And now I'm going to slowly move this up until the readout says 27. We'll see how well I can do this live. Because what I want is I want that sample to be perfectly flush with the end of the tube. 26.98. I'm going to call that good enough for what we're doing here today. But you can see, hopefully, that sample is right at the very edge. So it's 0.02 of a millimeter, maybe a little bit too far this way, but we'll call it good enough. But that digital readout helps me make very repeatable, accurate measurements. So now my sample's at a very accurate, precise, known location in there in terms of distance from our microphone, and we can now make our actual absorption measurements. So I move over to this tab up here. This is where I'm actually going to make my measurements. Now again, typically I would make multiple runs and average those runs. For today's experiment, I'm just going to do a single measurement, and I'll compare that to the reference curve that we got from the manufacturer and see if I've got everything set up. It's a good sense check before you test an unknown material to always do this, just like a calibration procedure. Make sure your system is operating how you expect it to. A couple more averages here. Maybe in post-production, we can speed this part up. Okay, so we're all done. Again, I could take multiple measurements. If I wanted to average them, I just hit this average and it just computes the average of all my runs. And you see my absorption coefficient here. So in my navigator, you see it keeps track of the H21, H12, and the HC that it calculated for me. It's got the time history for my run, and then here it's got my absorption coefficient. Okay, so I can just plot that. And so here it is, my absorption coefficient between 100 and 100 hertz all the way up to 5,700 hertz. You see it does pretty well somewhere in here at the, let's see, right around 3,200 hertz. It's 0.98, so it's almost absorbing all of the incident sound energy there. Now, just to sense check myself, I have a reference sample stored. The manufacturer provides this to me, and I brought it into test lab, and I can drag and drop that on there. And you see we get pretty darn good match between the measurement I just made and the reference sample they provided. Now, this is the reference here, and you see a little bit difference down here in low frequency. One of the things I did not do that the software was suggesting I do is back here on the setup page, it says, please allow the test sample to warm up by switching on the source for 10 minutes or more before your first measurement. Now, obviously, I didn't do that part, and so that's something I could do to improve the measurement quality. I could certainly take some more averages here, but all in all, this gives me a pretty good feeling that yes, I have the tube set up correctly, and I'm ready to test maybe a new material that I haven't tested before. Okay, so that's sound absorption testing using an impedance tube. Pretty straightforward, I think, with some center test lab. So we'll jump back in here and take a look at the rest of our slides. So transmission loss in a tube, you see it's essentially the same first half here. So again, you purchase an impedance tube from us, you can either do just the absorption half, or you can do the sound transmission loss, which includes a second half, some additional microphones. And the reason for that is now we're going to have a sample or a barrier or an exhaust system or something. Our sample, we need to measure with 2 microphones before that, or upstream of it. Here's the speaker over here, as well as downstream or past our sample before we hit this termination, right? We want to understand the incident sound power over this side as well as this side, so we can see how much might be getting bounced back, how much might be getting absorbed, and then how much is getting transmitted. Okay, so now we have 4 microphones, and so we have 4 microphone holders, and all those same dimensions will be set up in the software just like we looked at for absorption, but there are more distances, more microphones, more phase relationships to be tested. There's a lot more microphone swapping with transmission loss. The software leads you through all of it, and we have a nice little diagram showing you where your reference microphone is as we move those microphones around and do all of the phase calibration. Okay, very similar. Software leads you step by step through it. Now you may have been thinking, well, what if you said I could use this on a muffler or an exhaust system or some sort of duct? What if the inlet or outlet pipes of my muffler don't match the diameter of my impedance tube, right? I'm going to have to do some sort of adjustment. And so you might end up with a situation like this, where we have these cones gradually going from the diameter of the tube up to the diameter of the exhaust system or the muffler, and then back down to the other side of the tube. The problem with doing this is, even if we had just a system where there was no exhaust component, but it was just the first half of the tube, the cone, the other cone, and then the other half of the tube, we would see a transmission loss effect of those two cones. Okay, so the cones, just like the expansion can, just like any piece of duct you put in between there, will affect the sound transmission loss at some frequency, no matter what. And so what we would like to do is be able to account for this and remove or subtract the effect of those adjustment or transition cones, and only assess the transmission loss of the exhaust component in the middle. Fortunately, in SimCenter Test Lab, you can specify the cone diameter and length. And so the more gradual you can make this change, if you're going from the 1-inch diameter of the tube up to a 4-inch diameter for your exhaust system, not uncommon. The longer you can make that transition, the easier it will be, and the more effective will be the backing out of the correction, because it'll be a nice gradual change and a nice linear system. But you can put any cone in here to geometry, and it will back out the effect of those cone adjustments that you're making for different diameters. Similarly, to moving the microphones around, we're also going to measure with two different end terminations. So we have the rigid termination like we used for absorption, as well as that anechoic termination that we use during our phase calibration. So we measure our exhaust system or our barrier or whatever it is here with both terminations, and that allows us enough data points to do the matrix calculations that allow us to calculate the transmission loss of that component that under test. Again, the software leads you through all of that, and the real benefit is that we have a single tube that can measure both absorption when appropriate as well as transmission loss for small samples. And again, these are typically for small samples or large samples when it comes to something like a duct and an exhaust system. Now, should we have larger samples, so a bigger square of carpet, or like I was saying, a couch or something, we might have to do what we call in-room testing. And there are some different approaches here. And we will use these two acoustic fields that we mentioned in the beginning, the free field, where there are no reflections, and the diffuse field, where there are really only reflections or a ton of reflections. We're going to use both of these in different ways to accomplish these two types of measurements. So if you have a large reverberant room, again, if you have one of these facilities, that's great. It's a big room. The walls are, again, usually not at right angles to each other. They're very highly polished and smooth to encourage the sound to bounce around. We have often omnidirectional sound sources inside, placed around the room, and these will generate, again, sound in all directions, and we get that high level of sound to bounce around in here. And then we have microphones at multiple positions, and then we will have this sample that we will add and take away to essentially measure the difference the sample makes in the room characteristics. For smaller samples, or maybe you don't have the ability to build or access a diffuse reverb chamber like the diffuse field large room, there's also this smaller version called an alpha cabin. Same exact principle, it's just built much smaller scale. So these are typically much smaller, 1.2 meter squared samples, so not such a big sample as you might have in the large room. And it works just as well for high frequencies. It's not perfectly diffused because of the size limitation for frequencies below 400 hertz, but if you have higher frequency concerns, or this is the best you have the opportunity to use, it can get the job done. Same exact principle, just a smaller scale. Now, in a diffusion room or a reverb room, we want to assess an equal or homogeneous sound field on this sample, right? And so we have this material sample that will be placed on the floor. We'll have some omnidirectional loudspeakers. In this example, this simulation I'm going to show you, there are 4 speakers at the top corners of the room, and then you see these wavy things sort of spread throughout the room. These are diffusers. These are things that, again, help the sound waves get broken up and bounce around in a more chaotic, even way, so that the sound field is as perfectly homogeneous as possible. And I'll show you a simulation here where we model the different air particles with these little blue dots. And we see they're all shot out in a spherical waveform from those 4 speakers, but it does not take long for there to be sort of a very chaotic reflection pattern. This is what we're looking for, right? In a diffuse field, acoustic field, is that the sound's coming equally from all directions, no matter where we are in the room. Okay, so this is how we would quantify our diffusion chamber is perfectly diffused, is that we get a nice even spread of our sound waves, just like is shown here. So how do we test this in the large room? We do something called T60 times. And so we have a diffusion chamber here, reflective walls in the floor. We'll have an omnidirectional sound source. We'll have these diffusers. And then this is our large scale sample here. And you see it can be removed. And we can test the bare room, and we can test it with the sample in as well. And so essentially out of this omnidirectional source, we'll place a high level of noise, shown here in green, and then we'll shut that off very, very quickly. And in blue, we're showing you the overall sound pressure level from multiple mics or even a microphone that's on boom that's rotating to be sort of spatially average. And so we shut off that sound, and you see the sound pressure level begins to fall. And we enter this nice sort of linear decay area here until all the sound bounces around enough till it reaches the noise floor. And so now there's no sound in the room, it's just the background noise. And so we reach this minimum level. The amount of time that decay takes is what we call our T60 time. So you see our sound level is originally up here. At this level, it goes, this is where our sound source stops. We wait 5 dB for that sound to roll off 5 dB. Then we start our stopwatch, if you want to think of it that way. And as the sound continues to fall, we're keeping track of the amount of time it takes for it to drop 60 dB. Okay, so this is why it's called T60. It's the time to drop or decay 60 decibels. That's where we would stop after we've dropped 60 dB, and then it will continue to fall to our noise floor. Okay, so that's the T60 of our empty room. Okay, so there's no sound sample in there, and we get the purple curve. Next, we would add our sample, and we do another measurement, and we'll get something like this, right? The additional absorption material will absorb the sound more quickly, and so that decay will occur more quickly. And so our T60 decay time, T2, with the material sample will be shorter than our empty room. And the difference between those two, T1 and T2, is the absorption coefficient. We have to do some additional math and take into account the volume of the room and some other things, but essentially that difference in angle of that decay is related directly to the average absorption coefficient for that material. We're keeping track of how much material in terms of area we have, how big the room is, and we do, again, multiple measurements and then get an average result, and that will be our average sound absorption coefficient for that material. And again, something like this will be a function of frequency, so we often report it in 1/3 octave band, so you'd have absorption coefficient per 1/3 octave band. And so you see it's going to be better at some frequencies than others, and you might be tuning your material or its thickness to work specifically in a given frequency range. Alpha cabin, similar mathematics going on. The principle is exactly the same. It's a slightly different measurement because you have this K factor that is a function of the actual cabin. This will be provided by the manufacturer of the alpha cabin. But again, if you don't have a reverb chamber or diffusion field, you can use one of these things and get similar results by making similar measurements. Now, transmission loss in rooms, again, for large samples or something like a barrier, got a front of dash for an automotive situation or a chunk of wall from your apartment building. You want to say, how well does this block the sound? Here we're using what we call a 2-room suite, and the rooms are right next to each other. They share a wall, and there's often a pass-through or a cutout between the two where we can install our barrier. So we would literally cut the front of dash component out of the body of the car, or we bring the chunk of our apartment wall and install it in here really carefully between the 2 rooms. Now in this setup, we have our source room where we have this omnidirectional speaker. We've got a bunch of microphones set up in here. So we're averaging the sound pressure on this source room. Again, this is a reverberation chamber, so we're getting the sound to bounce around as much as possible. We want the measurements at all of these microphones to essentially be exactly the same. On the far side of our barrier, again, this is where our sample is. On the far side, we have another reverberant chamber, making a bunch of microphone measurements. And again, we want this to build up to be a diffuse field as well. And then we can essentially look at the difference between these two diffuse fields, and the difference will be responsible, correlated to the transmission loss of this barrier. So that's sort of a two-room reverberant method. And there are some ISO standards 140-3 that can lead you through how these measurements are made. I'll leave this in the presentation. Certainly, if you do this sort of testing, you will be familiar with the standard. The standard lays out all of the specifics for making the actual measurement. And that's all I have. Thank you for coming today.